Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
This is the third part in the Engineers Engineer series, talking primarily about signal integrity and PC board layout as it pertains to electromagnetic fundamentals. So the purpose is to provoke a consciousness of and thinking about electromagnetics and signal integrity up front, to provide a general framework upon which you will have the ability to build, and to open a box of possibly new vantage points for looking at electromagnetics and signal integrity. To make signal integrity on PCBs feel more intuitive and hence welcome, we have to understand the topics, but we don't have to present them with a huge amount of mathematics to have a basic understanding of them. That's what we're trying to do here today. Why intuitive? Well, first of all, there's a tremendous amount of material out there. For example, Lee Ritchie's Right the First Time and Howard Johnson's High-Speed Digital Design, Bob P's, there's app notes everywhere and calculators. This course today cannot be a substitute for really knowing and understand those, and I would encourage you all to start doing that. However, oftentimes it's difficult to see the forest for the trees because there's so much mathematics involved. So I'm trying to do today specifically without mathematics and to try to give an intuitive feeling. Oftentimes we need to look at a printed circuit board and scan for problems fast before trying to calculate solutions to fix them. Otherwise we'd be spending all of our time calculating. Much of the thinking is like a new box of vantage points. Often we need to think outside the old box in order to see things clearly, and 9.Connects experts can help you see things in different ways. We're going to talk about the role of quarter wavelengths. We started this in our prior discussion last time, a month ago. We're also going to be visualizing a few PCB problems, looking at a couple of things having to do with high-gain analog circuits, a couple of things about when to terminate signals and when not to, and characteristic impedances and reflections. Lastly, we're going to touch on a topic that no one seems to be talking about, and that's miniaturization and the effects that it has on electronics in the world today. So as a quick reminder, superposition and vector addition are very, very important. You all kind of know it, but you may not think so. For linear fields like electromechanical fields, the field at any given point is the vector sum of all the fields created by a whole bunch of individual little sources. It turns out a vector sum is merely the arrow sum of all the different things, since they have both direction and magnitude. So if I have a bunch of electric fields that all contribute some direction and magnitude, the resulting field is just the vector sum of those, i.e. stack the arrows all hiney to head and see where it ends up. Okay, let's talk about quickly scanning. What about distances with respect to a quarter wavelength? Why is this important? Well, first of all, coupling drops off with separation automatically. I mean, if you take a signal from here and you go 200 miles away, it's not going to be very strong. But it turns out that coupling, when you're close to something, is more a function of wavelength, and in particular, a quarter wavelength. So what is an approximate wavelength? Well, a wavelength has to do with how fast the signal is propagating. In free space, it's one speed on a PC board. It's a little bit slower. But if you say, well, how many cycles are there per second and how far it goes in a second, well, if you divide the two, you can come up with the wavelength. So what is the wavelength of a quarter wavelength of a clock signal? Well, that's a trick question because first, a clock signal is not a sine wave, so it actually has many, many harmonics arising from both the basic clock rate, i.e. A million clocks per second, and from the edge rate that says it's changing in 10 nanoseconds. So the harmonics from both of those need to be considered. Waveforms have multiple frequency components called harmonics, and which ones must we consider? We need to consider all the harmonics which have significant magnitude. And why a quarter wavelength? Well, if you remember from last time, we talked about the Eiffel Tower and about quarter wave antennas. A quarter wavelength is the shortest resonator for a low and a high Z impedance point. Like the Eiffel Tower, at the very peak, it can't have any currents flowing out of there because there's no path. It's in air, which is an insulator. But it can have very high voltages because of the capacitance that's there. Similarly, at the base, it can't have any voltage because it's sitting on ground, but it can have high currents. And in between, the voltage-current relations vary. So going from a low impedance point like the ground to a high impedance point like the top, we end up having a quarter wave resonator. This happens all the time on PCBs where we have grounds and where we have high impedance signals. For example, if you have a driver to a receiver, the driver acts like a low impedance and the receiver may be a high impedance. If so, you have a quarter wave antenna. We can also talk about a half wavelength for the shortest resonator for too low or too high impedance points. But really a half wavelength is nothing more than two quarter wavelengths stuck end to end. So quickly spanning, what is the spacing between them? Is it small with respect to a quarter wavelength? If so, that's good, because it means that if you have two lines, wires, let's say, with equal and opposite polarities, they cancel fairly well because they're very close together. So it cannot radiate at most angles of radiation. However, it turns out if you have them significantly far apart, that is bad because now there are many different directions where equal and opposite signals can radiate, and they can also be subject to receiving signals or to be noise. So we're trying to keep things small with respect to all signals that have a wavelength of a quarter wavelength of all frequencies of interest. The same thing is true on a PC board. If we have a couple of traces that are less than a quarter wavelength apart, that would be good. If they're much more than a quarter wavelength apart, that's bad because, again, they can transmit and receive. If you have a PC board where the trace is above its reference plane by much less than a quarter wavelength, that's great. If it's much greater than a quarter wavelength, that's bad. Well, it turns out you're probably not going to have a board like that because the boards are not very thick, and so the frequencies you'd have to be at probably would not be made on a board that you would be considering. But it turns out that if you have all of your spacings are large with respect to a quarter wavelength, it's just not a good thing. Let's take a look at a sample PC board. Here's one that we can look at. Let's see if we can quickly look at it and examine it for some potential problems. First, what's the layer stackup? Well, we notice there's 8 layers, and it looks like there's 5 signal layers and there's 3 plane layers. When I look at the stack up in the middle, it looks like they're off-center. It looks like I have 3 signal layers, followed by 3 plane layers, followed by 2 signal layers. If so, this would be an asymmetrical stack-up and not good because it would be have a tendency to warp when it's made because there would be excessive copper on one side than on the other because planes are pretty much all copper and signal traces are pretty much all not copper. So a warning flag goes up here. Also, it should be noted that the signal and plane layers are not interleaved. If they're not interleaved, that means they're going to have trouble acting as a ground reference and for isolating the signal layers from each other. So let's take a little bit more look at these internal plane layers. They look very much like normal plane layers look. They have negative artwork, mostly copper. There are no routed traces on them, and there are contiguous areas grouped and assigned to various power nets. It's only on the right that we see some various tracks that actually separate some of the power areas. If you look a little closer, you'll start to find that there are some very narrow necks, less than the manufacturing tolerance, and there's a few little islands. These can be a problem. However, in neither case do they appear to be an electrical problem. For example, if the narrow necks on the left could not be made and the copper was completely eaten through, it would still be connected around the other side of the vias. And similarly, for the little island on the right, it's so small between the vias that it probably wouldn't be a problem for any SI. But it's worth looking for them, and it's worth checking to make sure. So let's look at the top layer. It looks like it's pretty much got a BGA-type part, maybe an FPGA or a micro of some kind, and a couple of buses coming down to the connectors. That's all well and good. But the first thing that should be noted is there's quarter wave stubs on here where it's tied to ground by one via, and then a bunch of copper is just kind of dangling out in the breeze. That's probably a result of the copper pour that they put on this layer and not having stitched all those ends down cleanly. As a result, they have a tendency to be able to resonate at certain frequencies. So is it a problem? Well, we won't know that until we decide what frequency they resonate and compare that to the fundamentals that we have in there and see whether it's a problem. If they're very, very short, we probably won't have significant energy. If they're long enough, they could create a problem. It also depends on how close they are to the signals in question. If they're very far away, they won't get stimulated by the signals. If they're very, very close, they get much more stimulation and coupling. If we have a problem, of course, we would then need to go through and either dampen them, which is hard to do on the surface. Sometimes you can paint on materials to do that, or you could put resistors on the other end, but that's rarely done. Alternatively, you could stitch them with vias all the way along so that there are no long quarter wave sections, or you could try to change their length, retune them to some other frequency, decrease the coupling by moving the signals away from them, or all sorts of other things. But if you're repouring a plane layer, that probably wouldn't work very well. So ultimately, we get down to the place that, well, probably the best thing to do is just make them so that they don't exist, make them go away. Let's take those same signals on the top layer and now view them by category of signal. We notice that we have a set of data lines in purple and the control lines in red and address lines in magenta. When we look at it that way, we see long parallel runs adjacent to each other. Well, those runs mean that there's a lot of coupling between those signals. Now, that may not be a problem if all of the signals transition at exactly the same time, but if they transition at different times, that could be a problem. So we would want to check and find out exactly how that works for this particular bus on this particular chip to see whether that's a problem, to check whether it's acceptable. And if not, then we would need to separate them, either put more gap between them or route them differently. When we look at the second layer, we notice that there are some traces running vertically. However, those constitute openings that are under the top layer. So a flag goes up saying we may not have a good ground reference for the signals. If we overlay the top layer back on there, we will see that those openings truly are underneath the signals run on the top layer. Hence, they're a problem. They interrupt the return currents on the ground layer, which is the second layer in this case, and hence they'll have to go all the way around, and basically it's going to get the signal integrity all bollocksed up on those traces. So that's a red flag that goes up. We can see that without running any calculations. Let's also look between the second and third layers. Clearly, there's more signals routed on the third layers, but the same areas that were cut out on the second layer are a problem for signals on the third layer. So we have a problem there too. However, it might be noted that the fourth layer is a plane, and so the presence of a plane next to the signals on layer 3 may improve it a little bit by virtue of giving the ground class a different side to go on, although it's generally not considered acceptable to have a ground plane on both sides and just remove one of them, especially when they're close to similar distances. Similar problem exists between the 7th and 8th layers. You can see signals going in both directions over the same place, and hence you have no plane reference. Note that this is referenced to layer 6, which is one of the plane layers, but that is not much of an improvement because, as you recall, layer 6 was the one that had the plane splits on it. So these signals would still be going over split planes. Again, these are problems that can be identified merely by looking at the board. Suppose this was an analog board. Let's change gears for a moment and talk about analog circuitry. In the typical analog circuitry, you'll have a lot of op-amps doing various things. Many will be providing gain, some will be doing filters and other things. But beware of high-gain paths. You can have paths where you go through a large number of op-amps, and the gain through that can be very high. It can be well in excess of millions. It can be in the billions. And if so, that means that any little bit of signal at the beginning is going to create a huge voltage at the end. Note that it may also split in the middle, and you can end up with multiple paths going to multiple outputs. If so, you have to consider that the cumulative gain can be extreme. There's no digital quantization to help. You don't have to say, you can't say, well, this is a 1 or this is a 0. It's a voltage that's analog. It gets amplified no matter what. It doesn't get truncated to a 0 or a 1. there's an extremely small amount of feedback that you can actually tolerate if the gain is that high. So you have to be careful not to let that occur unless it's intended. Keep the layout linear. Don't wrap or fold back. If you do wrap or fold back the output towards the input, then there could well be enough coupling that the circuit could oscillate or it could have spurious responses that you really don't want. And most importantly, pay attention to isolation, shielding, and decoupling. You can always add shielding over things to try to get rid of stuff going through the air. You can isolate as much as possible the signals from each other, but also watch for things like power lines that run all the ICs, over which a certain amount of energy could just propagate from the output back to the input. So all of these are very important. And most important, keep the input away from all noise sources because it's all going to be amplified. So is termination needed or not? That is the question. Many approximations and pet rules abound. For example, when the time that it takes to propagate from one end of a wire to another is greater than half of the rise and fall time, whichever is the largest, then that would be a place where you really want to terminate that signal. Another one that's related to it is if the length of a track, which is divided by the maximum rise or fall time, is greater than 2 inches per nanosecond. Of course, that makes some assumption about the speed of propagation on your board, so you would want to tailor that for the type of board and the type of dielectric material you have. It's also been stated for analog, you should always use rise and fall times is equal to 0.35 of the frequency. But basically, that's a 90-10 rule on a sine wave, which sounds something like a digital engineer trying to understand analog. It is true that you do need to solve them, but 90-10 is not really quite the right concept to apply there. So in reality, ideal digital waveforms require infinite bandwidth, i.e. they have sharp vertical sides and flat tops, and very sharp corners as a result of that. That takes a huge amount of bandwidth. Real digital waveforms approximate that. They do require and have a large number of harmonics. Reflections always occur at any change in characteristic impedance. The question is whether the signal will be, not whether the signal will be terminated, it will be. It's only when, where, and how ideally, or how cleanly. Ideally, all harmonics of the signals should be terminated in a controlled fashion. So is termination needed or not? What are the key criteria? Well, for digital signals only, it's okay to distort the wave shape in amplitude as long as the waveforms can be reliably detected as a 0 or a 1. It's also okay to distort the spectra as long as the waveforms can be detected as 0 or 1. And similarly, you can distort the wave shape in time as long as you can detect a 0 or 1. That's key because it is digital. It does not apply to analog. Therefore, it applies to clocks as well as provided above, provided that you're able to meet the hold times, the setup and hold times, and you don't have any missed clocks and no extra clocks occur. There's also some special differential assumptions. It's okay to distort the differential amplitudes as long as waveforms reliably remain in the common mode range. Get outside the common mode range of the amplifier, the output can invert. It's okay to distort the differential relationships as long as the waveforms reliably cross over each other only at the appropriate time. That's primarily for clocks. So if you have a differential clock, the voltages will be wandering up or down or doing whatever they do. But when they cross within the common mode range, that's when you clock. And you need to make sure that those are maintained. Based on these distortions being acceptable, all harmonics summing to less than a particular amplitude, a particular amount of energy, can be thrown away. For trapezoidal waveforms in, say, the 30% to 50% rise time to period range, and say less than 5% error in voltage, such as LVDS, it turns out the seventh harmonic related to the edge rates is what you need to retain. This is fairly common. You can also have some signals that have much lower frequencies, but in which case you'd have to retain a lot more. But again, since LVDS is geared towards trying to translate high signals at high speed, it doesn't allow you to have it allows you to use almost a trapezoidal signal, a very trapezoidal one. In this case, the bandwidth can be reduced down to only those 7 harmonics and contain the distorted signal. Okay, here's a couple of spreadsheets, the one on the left has a different set of rise times, where the rise time is the on time over 2. The one on the right is the rise time equals to the on time. The one on the left is the target for an LVDS when it comes out of the source. The right one is the target for an LVDS at the end of a long cable so that it can be properly received in an IF diagram. If you go down and look at the harmonics, you'll see the residual energy has dropped to less than 5% on both of them by the time we get to the 7th harmonic. Therefore, let's take a look at this. If you only have the first harmonic to a trapezoidal waveform approximation, it's, guess what, a sine wave. So if you add in the 3rd harmonic, it starts to look a little bit trapezoidal. Add in the 5th harmonic, and now you can really start to see it. Add the 7th, and you have something that really clearly resembles a nice, clean harmonic wave. If you throw in the 9th, it's even more cleaner. It's now starting to work a little bit on the corners, and it has a little ripple on the top. If you go past that, say to the 11th, or even to the 13th, you start finding that what it's trying to do is it's trying to map out the little corners, and hence it's putting in some extra waves, which are still less than that 5%, but attempting to try to make that so that it will, so that you can actually get the square corners. We really don't need the square corners, hence the 7th wavelength is the most important. Let's switch topics a little bit and talk about traces with a pad in the middle. If there's a pad in the middle, it's probably a different width, and so you're going to end up having a change in impedance. Let's say we have Z0 for the trace and Z1 for the impedance. Doing that, you can calculate the reflection coefficients. The reflection coefficients will be very similar going from Z0 to Z1. However, if you notice, if Z1 is equal to Z0, i.e. if it's the same width, the reflection coefficients are both 0. So there are no reflections. However, if you do have some change, note that the reflection coefficients before and after at both edges of the pad are equal and opposite. That brings up some interesting possibilities. If the reflection coefficient is fairly small, so that most of the power at P1 is approximately the same as P2, then the reflections will be similar sized but in opposite direction, and hence most of it will cancel. Thus, the power out is almost going to be equal to the power in. There won't be a lot of reflection. However, this is based on the quarter wavelength being much, much longer than the pad. Otherwise, you will have a problem. If this is true of signals passing pads or vias, unless the wavelength is very, very short. If at high speeds, such as digital signals that have many, many harmonics far, far higher than the bit rate, these harmonics may be reflected to some degree because their wavelength is much shorter, even if the fundamental is not substantially reflected. Hence the ability to see these on many time domain reflectometers. Let's talk about miniaturization. Miniaturization is both a boom and a bane. It has historically been good because things were unnecessarily huge. I remember a long time ago, I won't go back and talk about when, but things were very, very large. Electronics came in huge cases. I remember the first TVs with the 6-inch screens that were like a large piece of furniture in the living room. They were too heavy to be moved, and it could also cost a lot. So miniaturization was good for that, but it started to go too far. Recently on a plane trip, I noticed a lot of people squinting at credit card site screens, trying to watch epic movies as they went on a flight, and reverting to tiny little styluses instead of their fingers to try to poke the buttons. It is going too far. They also sit there straining at anemic sound crammed up to the side of their heads, and it's pretty clear that most of the electronics has been designed to be so small that it no longer really fits human beings or their normal motions or things that they can do. So it is kind of a bane. It also is everywhere. Forms of miniaturization include things such as very tiny cars. I see people with cars that are barely over 8 feet long, and they're in there going 80 miles an hour down the freeway, and if they get into a crash, they're dead meat. Smaller keyboards where you can't fit all the keys on and it's hard for your fingers to fit. Smaller tools. I have a drill that was purchased by my father back in 1960, and it's still running. It's a little heavier, but I've gone through about 10 drills from other manufacturers since. That old Monkey Ward's drill will last forever because of it being a little bit sturdier. We don't have that anymore. I remember 2x4 lumber being 2 inches by 4 inches. Now we have smaller dollars, we have smaller freedoms, smaller utensils. The knives, forks, and spoons my parents had that were cheap back then are now way more and are much longer than the ones that I can buy today. There's smaller budgets and even smaller thinking. Well, tiny cars have been causing accidents. It's gone too far. Unrepairable electronics are now being thrown in mass into our landfills and polluting them with lead and other things, hence the movement for ROHS. Again, it's going too far. And PCB problems and costs due to minimizing size are, again, going too far. It does look like a beautiful apparition. Smallness is ascribed the attributes of lightness, beauty, state-of-the-art, reputation, even reliability. Smallness is unquestioningly believed to be a fount from which all sorts of product goodness flows. Everybody who has been brought up through the ranks uses smallness as a measure of their designs. Have you ever seen an engineer who's finally completed a design on a tiny board come out and look at it like they have a baby? Well, it's exceptionally true because it's small, and that's oftentimes talked about as one of its attributes. Any other option is intrinsic. Any other opinion is intrinsically deemed archaic, wasteful, and counterproductive. This is also universally known, and hence arguments against it, to the contrary, are considered pointless. Try to talk about somebody about making a board a little larger. However, is this really true? Let's think about it. The ultra-miniaturization of PC boards. The formula for failure. Smaller costs more for precision processes. Smaller makes manufacturing tolerances harder to meet. Smaller process limits increase failures and scrapping. Smaller worsens capacitive cross-coupling. Smaller worsens inductive cross-coupling. Smaller worsens feedback and noise. Smaller leads to worse performance. Smaller takes exponentially longer to implement. Smaller takes exponentially longer to debug. And smaller makes changes harder or more impossible to do without starting over. That's the truth. What about proper sizing? That is the formula for success. We'll start with only choosing tray space widths widely available without any extra costs or steps. Choose packages which are commonly available without any extra costs or steps. How many people have taken the smallest part and put it on the board only to find out that this one happens to have a ground pad in the center that they need for thermal to get heat out of the part, and therefore they have to go to extreme measures to try to get that heat dissipated in the board through thermal vias. Only choose two-pin parts sufficiently large to be easily reworked, like 0201s. Huh? How about at least 0402s or maybe 0603s? It really would help. Leave room for test points on all important nodes for testability, rather than throwing them all out and then wondering how you're going to test it later. Leave room for commonly legible silk screens, something on the order of 30 mils by 4 mils, or else eliminate these altogether. Leave clear margins around larger part parameters for rework station heat shrouds. How many times have board houses needed to rework something and only found that they have to remove 20 or so capacitors from the outside of a BGA before they can get the heat shroud on it to get the part off, rework the balls, and put it back on? Putting those parts in that place is not designed for manufacturability. So all of these are problems with going too small and things that can be started by thinking about it when you're going into a design early on. So what should you be thinking about for proper sizing? Only place components loosely to ease the adjustments as you're doing design. Only place components where directly associated circuitry is or will be placed on the directly opposite side. It's not good to place a switching power converter on one side of the board and put a very sensitive electronic circuit, analog circuit, on the opposite side. Copper has a finite conductibility, and electric fields and electromagnetic fields will go through it, and even resistance changes as currents are flowing through it cause a voltage change as seen on the opposite side. So they're not completely isolated. And it's also much easier and cleaner to do a two-layer design than doing two one-layer designs on the same PC board. Leave significant unpopulated gaps between sections of circuitry not specifically interconnected. We're always trying to reduce crosstalk and noise between things. Well, how do you do that? Well, you leave some gap between them. So start off by allowing there to be a gap. Add space for standoffs, supporting ledges, mounting holes, edge back-off tolerances, expansions, fiducials, tooling holes, etc. Add that in. Get it in there in the beginning rather than trying to tack it onto the board after it's already been laid out. Consciously add some percent spare area for future growth, because it's bound to happen unless maybe this is the final rev of a 7-rev board and it's going into production the final time. 50% is common, but your mileage may vary with possible expansion. Fight for this amount of board area. It is justified, truly. So what are the results of insufficient PC board sizing? Failure to allocate sufficient board space in the beginning inevitably leads to compromises later. These compromises always come in areas less visible and less thought of up front. What are those areas? Signal integrity, noise immunity, thermal performance, serviceability, etc. Those are the things that suffer as a result of not giving yourself sufficient board space to start with. So what about going 3D? If there's an insufficient area to make a proper board, then consider going 3D. With that, I'll just throw out one possible option that I think is worth considering. I've used it, and it worked quite well. Design a PCB which can be split and stacked. Board-to-board interconnects happen to be fast and cheap. Fab it as one board, populate it as one board, and as a final step, split it apart, stack it, and solder the interconnects. The costs are almost identical. So consider we needed a board this size, but are told that, no, we really don't have that amount of area. Well, okay, add some V-scores, move the mounting holes, then add some corner cutouts around the other parts, add some board interconnects, populate it with the rest of the circuitry as you would normally populate it, and the same as before, stab it the same as before, assemble it the same as before, and finally, as a final step, break it apart, stack it up, and do some simple soldering to put it together. Treat it as just one assembly. More area, just a different form factor. Resist the temptation to consider this for boards. So in summary, PC boards are filled with conductors of all different types, and depending on their length, termination, and proximity, any of them can be resonators. If they resonate, they can radiate or distort signals. Their sensitive frequencies can be calculated. Keep circuitry spaced and separated. Radiation and susceptibility problems can be solved early by knowing what to look for. An intuitive vantage point can help spot these quickly and determine whether or not they need more study. It can save you a lot of time. In summary, the experts at 9.Connects are here to help you in all phases of your project. That includes brainstorming, theory, conceptualization, as well as planning, engineering, layout, and troubleshooting, and even rollout to production.